Hello my dear friends, welcome to Adventure Story channel, and today my dear friends we will continue our LNG training course. So this is not only for LNG, this is also for the tankers. This knowledge it's very necessary for all marine engineers. If you like to increase your knowledge and to see something different. And I know that there is also a lot of video tales on board available, but as I have seen, not all the chapters is available. As I have been on board also and checked, mostly for marine engineers there is some chapters, but Videotel have a lot of programs, have a lot of chapters, and really it will be nice if the companies will update the booklet and the chart with the video tales. It will be really nice to participate there. So let's start here in this chapter, knowledge of main design principles. So let's go.
As indicated in the previous unit, the objective is to prevent any leakage of cargo affecting the ship's hull. The design of the tanks and the choice of construction material is planned to prevent leakage. Secondary barriers and drip trays are provided to protect the ship. Some LNG carrier designs include steam heating coils in the cofferdams to further protect against embrittlement of the hull. The purpose of the secondary barrier is to provide temporary containment for any envisaged cargo liquid leakage for a period of up to 15 days, unless other specific requirements exist. The objective is to prevent leakage through the primary barrier from lowering the hull steel temperature to an unsafe level. The secondary barrier must fulfill this at a static heel angle up to 30 degrees, and its effectiveness should be capable of verification after the ship has entered service, for example by a pressure vacuum test or visual inspection. The mechanism of primary barrier failure must not cause secondary barrier failure or vice versa. The secondary barrier must be capable of being tested periodically after the ship is in service.
So we have a lot of information here, and for all this information, for sure the company will have specific papers for checking, for testing properly, for certificates and such kind of things. That is true. But to knowing such thing that persists, it's really important. So you'll be aware. You will always have this awareness. And let's see together what we have here: water ballast or void space, some of the construction, water ballast down below here. Here what we have: inter barrier space, as you can see it holds the gases, the primary barrier which is inside, the inter barrier space, the inner hull, and the insulation, and then secondary barrier, which is this one here. As you can see, there is a lot of barriers, there is insulations, so will not be affected by the temperature, the outside temperature. And let's see the other tank. We have two types, A type and B type, which is here. So let's see again: pipe column, which inserts inside on the tank, cross section of equatorial ring, cross section, weather cover, which is this, insulation. We have shown our insulation, ballast space, ballast also here, cargo pumps, pipe column connection to shell, metal foil to aid bonding, and pipe column again. So We have bimetallic joint here, stainless steel, carbon steel, different kind of metals apply on the construction. As we can see, it's really specified. The construction is really careful, and have improved through the time. It's really nice to see so much details. Let's move on.
There are two main designs of containment system. Independent tank type B. Integral membrane tanks. Independent tank type B. The Moss containment system consists of large, spherical aluminium or nickel steel tanks. These tanks are self-supporting and are secured around the equatorial ring. All pipework and equipment is carried in a central pipe tower. Tank insulation is provided by polyurethane foam or expanded polystyrene. The insulation barrier surrounding the tank is filled with inert gas, which helps avoid the problems of ice formation, as well as providing safety against fire risks.
So this is kind of protection, have this kind of independent tank type. So we have a supporting skirt here, we have the hold space, which is here, we have the polyurethane insulation, we have 9% nickel steel primary barrier, steel dome, and also the inner hull, which is here, and water ballast down here. So let's move on.
The IHI SPB system consists of an independent prismatic tank made of aluminium. The system resembles a standard LPG independent tank structural arrangement, with the support provided by internal stiffening and web frames. The tanks sit on fabricated support seats and are held in place by a system of chocks fitted around the exterior of the tank. As fracture analysis has proved that, if a leak occurred, it would not cause total failure of the primary barrier, independent tank type B systems are permitted to have only a partial secondary barrier. This partial secondary barrier must be arranged so that primary barrier leakage is deflected into it and prevented from cooling the hull excessively. The extent of the partial secondary barrier may take account of liquid evaporation, leakage rates, and other relevant factors.
So let's see. Water ballast around here, hold space, double bottom tank, secondary barrier, cladding, primary barrier, bulkhead, and foam insulation.
Integral membrane tanks. The concept behind this design is to use the strength of the ship's double hull to provide the support for the cargo mass. This means the cargo tank itself can be made from an extremely thin metallic membrane, as it only has to provide liquid tightness. The membrane must be supported by the hull structure through load-bearing insulation. The fundamental difference between the membrane systems and the independent tank types is that the membrane is subject to the same deflections and stresses as the hull when at sea. For this reason, the secondary barrier of a membrane system has to be designed in a different manner, so that any failure mode that damages the primary barrier will not breach the secondary barrier as well.
So let's see how it made. Isolation and secondary barrier, inner hull, primary membrane, and water ballast here. So let's move on.
The Gas Transport and Technigas GTT NO96 membrane system incorporates thin layers of special steel known as Invar. Tank insulation is provided by plywood boxes filled with perlite, a powdered mineral. These also transmit the cargo loads to the ship structure. Nitrogen is passed continuously through the insulation spaces to disperse any minor leakage and to keep the perlite both suspended and dry. The GTT Mark III system uses a primary membrane of corrugated stainless steel to allow for the expansion and contraction required on cooling and warming during the ship's operational cycle. The primary insulation consists of polyurethane foam laminated with a thin plywood facing, and the membrane is welded to stainless steel strips set into the plywood. The secondary barrier is provided by a sandwich of aluminium foil and GRP, attached to polyurethane secondary insulation, which is also backed with a thin plywood layer. Nitrogen is again circulated through the interbarrier spaces.
So we can see how specified can be these cargo holds and how must be protected the cargo from the leakages and also from the other effects like stresses from the weather, from the sea. Everything must be taken in consideration.
Survivability. A number of arrangements are provided to resist the effect of damage. For example, the hull must be subdivided by transverse watertight bulkheads to provide sufficient reserve stability and buoyancy after the specified damage occurs. Cargo tanks that are independent of the hull also have to be fitted with anti-flotation arrangements to resist the upthrust caused by flooding of the hold to the summer load line with the tanks empty. Suitable supports also have to be provided to withstand the effects of a collision both in the longitudinal and transverse directions. Double bottoms must be fitted, and longitudinal bulkheads to form side tanks are also required.
So let's see, let's press here, auxiliary hydraulic unit. Let's see some of the spaces. Let's press here, system control, hydraulic prime mover, hydraulic prime mover, crane, submerged ballast pump, like Framo pumps, cargo heater, deck machineries, and both thrusters. So let's move on. Let's take our test. Let's see what we have seen and what we have learned. The second barrier should provide temporary containment of any envisaged cargo leakage for up to 10 days. That is true. Integral membrane tanks use the strength of the double hull support the mass of the cargo. Integral membrane tanks, if I remember, that is true. Independent tank B ships are permitted to have only partial secondary barrier. True. The GTT integral membrane designs for LNG carriers requires the circulation of nitrogen through the interbarriers. Yes, that is true. Let's see what I have done. Maybe I have made some mistakes. Yes, I have made, and let's see which one. The second barrier should provide temporary containment of any cargo for up to 10 days. Okay, that is false, and this is the nice to see in such courses. So let's move on. Let's see which one we have finished here. Demolition. So we have not finished also this one here, okay, which is also very, very important. One moment again, principle of design. Okay, we have finished this. I will go again here to the physics. Let's see the gas laws.
Pressure and temperature relationship. Much work was done on the subject of gases at the beginning of the 19th century. The Irish scientist Robert Boyle, for example, measured the volume of a gas while he varied the pressure on it, keeping the temperature constant. The French physicist Jacques Charles kept the pressure constant and then measured the volume while varying the temperature. He found that as the temperature rose, the volume increased in a straight line relationship. Although scientists then could not produce extremely cold temperatures, the graph showed that, in theory, there would be a very low temperature when the volume of gas was zero. Repeating these experiments with a variety of gases showed that whatever the gas, the temperature at which the volume became zero was the same. This temperature was defined as the absolute zero of temperature. The absolute scale was named in honor of the physicist Lord Kelvin, and this temperature scale is given the origin point of 0 degrees Kelvin. The Kelvin scale has the same interval degrees as the Celsius scale, but the 0 point is 273 degrees below 0 Celsius. It is not entirely clear what happens to atoms at the absolute zero of temperature. It can only be approached, never actually reached.
Yes, that is true. It's really a low temperature, which take a lot of years until we can reach it.
The work of the early scientists on gases resulted in a number of gas laws, which defined the relationships between different properties of the gas. Boyle's law, for example, states that pressure times volume is constant if the gas is held at constant temperature. P times V equals a constant. Charles' law states that volume divided by temperature is constant if the pressure is constant. V over T equals a constant.
Boyle's law, Charles' law, so let's move on.
The pressure law, sometimes referred to as the constant volume law, states that pressure divided by temperature is constant if the volume is kept constant. P over T equals a constant. Another scientist who contributed a great deal to our understanding of this area was the Italian Amedeo Avogadro. In the early 19th century, he proposed that the volume of a gas could be related to its mass. At 0 degrees Celsius and 1 atmosphere pressure, he found that for different gases, a volume of 22.4 litres always held a quantity of gas equivalent to its molecular weight in grams. Avogadro defined these conditions as normal temperature and pressure, or NTP. So, 16 grams of methane or 44 grams of propane occupied the same volume at NTP.
Very interesting.
Furthermore, Avogadro proposed that this volume contained the same number of atoms or molecules for any gas, a number he calculated as 6.023 times 10 to the 23. He defined this quantity as a mole, from the Latin for a large number of molecules, and defined the volume occupied by a mole of a gas at NTP as the molar volume. Note that Avogadro's hypothesis is independent of mass units, so it is possible to define a molecular number and a volume for kilograms, pounds, and so on. However, the gram mole is the most commonly used, so it is the unit assumed if no other is stated. By putting these various gas laws and Avogadro's hypothesis together, it is possible to derive the general gas equation that relates the pressure, volume, and mass of a gas to its temperature. N is the number of moles of the gas, and R is called the universal gas constant. The other law which describes the behavior of gases is known as Dalton's law. Dalton found that if he took a mixture of gases which did not react with each other chemically, then the pressure they exerted in a closed container was independent of the mixture. That is, each gas behaved as if the other components of the mixture were not present. This can be simply illustrated for a mixture of hydrocarbon gases as shown. P is the total pressure of the mixture. P1 is the partial pressure of the methane present, P2 is the partial pressure of the ethane present, etc. Finally, we need to be clear that in calculations involving the gas laws, we use absolute units of pressure, whereas in general industrial practice, we measure pressures relative to atmospheric pressure. So, gauge pressure shows pressure above atmospheric pressure, and the absolute pressures used in gas law calculations are 1 atmosphere higher than gauge pressures.
So also it's very important that say here about the gauge pressure that shows the pressure above the atmospheric pressure, and the absolute pressures used in gas law calculations are 1 atmosphere higher than gauge pressures. So this you must be careful on your academy, on your school, for your calculations, to make it clear. It's really important. So let's move on.
The laws of thermodynamics. In using the cargo systems on board, we also need to understand some of the laws of thermodynamics. There are 4 of these laws, although only 3 concern us here. The 0th law introduces the concept of thermal equilibrium between bodies. It states that if a body A is in thermal equilibrium with body B, and body B is also in thermal equilibrium with body C, then body A is also in thermal equilibrium with body C. The first law introduces the concept that heat and work are equivalent. It states that the heat lost from a source is equal to the total heat gained and work done on the bodies that receive that heat. The second law introduces the concept of directional heat flow. It states that heat always flows from a hot body to a cooler one.
Yes, that is true. I also have seen this in practical, that the heat always flow. If you take a big pool and you fill cold water inside, and after you add a very hot water, you will see how this hot water moves to the cold one, how drag to catch and give its heat to the cold one and starts one kind of rotation inside the pool. That is true. Let's see these interactive buttons together. Thermal equilibrium, heat equals work, and hot always transfer the heat to the cold. Let's move on.
Joule-Thomson effect. When a perfect gas flows through a nozzle with constant inlet and outlet pressures, the temperature of the gas is the same before and after it flows through the nozzle. There is a temperature drop, however, during the passage of gas through the nozzle itself. At this point, internal energy is transformed into kinetic energy, with an accompanying temperature drop. However, for real gases, there is a sustained change in temperature, even though the energy content of the gas remains constant.
Joule-Thomson effect. So when a perfect gas flows through a nozzle with constant inlet and outlet pressure, the temperature of the gas is the same before and after it flows through the nozzle. There is a temperature drop, however, during the passage of the gas through the nozzle itself. At this point, internal energy is transferred into kinetic energy with an accompanying temperature drop. However, the real gases, there is a sustained change in temperature. Even through the energy content, the gas remain constant. Very interesting. So let's take our test. Let's see what we have learned. When gas flows through a nozzle, the temperature will when gas will fall, I believe will fall. Charles' law states, Charles' laws states Vt equals C. Which law of thermodynamics states that heat always flows from the hot water to the cooler? The second law. The general gas equation combines the gas laws with Avogadro hypothesis. If I remember correct, this is the correct formula, this one. So we have been correct in all these four questions. We have answered properly. So we can check what we have finished here. We have finished also gas laws. Most of these formulas we have made sure in the academy. That is true. There is a lot of practical tests there, a lot of things that you have seen, and the books really talks about and describes all these laws. It's very interesting to know that kind of laws, so you will be better understand what is going on your system, and better understand what problems can be formulated from these operational criteria. So thank you again, my dear friends, that you have stayed. We will continue in the next videos in other days with the next sections, and I hope you like such kind of videos. I like also you to comment down below what you believe and if this video helps you. So see you in the next video. Bye bye from Adventure Story.